So we've seen how to compute improper integrals now for some specific examples. One of the things that we'd like to do, though, is generalize a little bit further and sort of look for patterns of integrals and see what kinds of integrals tend to give convergent values and which ones tend to diverge. So we'll start with the family of exponentials, and then we'll look at polynomials next. Let's take a look at the integrals from 1 to infinity of e to the kt dt. And as we do with all these examples, we're going to use our definition first and replace that infinite interval upper limit with some upper limit that's a constant. And then afterwards, we're going to let that upper limit get pushed towards infinity. Okay, so now we just have to do an integral of e to the kt. We don't worry so much about the limit. We'll keep copying it. We'll evaluate it later. But right now we just need to find the antiderivative of e to the kt. Well, that's e to the kt again, and divided by k. Remember, if we differentiate this way, we'll get back to what we started. We'll get a k out top, k in the bottom will cancel. It was a definite integral from 1 to b, so we're going to evaluate that at 1 and b. Keep copying, limit as b goes to infinity. 1 over k is out front of everything. Then we have e to the k. B is going in for the time value. We're doing a time integral, so b goes in for time, minus putting in 1 for time, e to the k. Okay, so that gets us what in the end? Well, now we have a simplified integral. The integral's gone, we now have the value. We can now ask the question, what happens as we push this upper limit of integration out towards infinity? Well, we have two cases here. The only b is here. So if we're letting b go to infinity, there's two things that can happen. If k is larger than 0, then we're talking e to the positive something times b. Well, that's going to go off to infinity. We have e to a larger and larger positive value as b goes to infinity. And that would mean the integral diverges. Okay, but what if that k value were negative? Then we'd have e to the power b with a negative constant something out front. Doesn't really matter so much what the value is because b is getting off and pushing off towards infinity. And so that's not going to go to infinity, sorry, that is going to go towards e to a negative large number is going to go towards to 0. You've got an exponential decay happening as b gets larger and larger and larger. So in this case, the integral will converge. So what we just said here is that if we see an exponential curve and we're talking about the area underneath it pushed out towards infinity, if it's a positive exponential, or e to a positive number times t, then not surprisingly whatsoever, we're talking about exponential growth there. And if we talk about the area underneath that curve, the area is going to be infinitely large. If we talk about any exponential decay, and it doesn't even matter how slow the exponential decay is, just any e to the kt, e to some negative value to the power t from 1 to infinity, this area will always be finite. The area underneath that exponential will always be finite. Okay, let's take a look at a slightly more interesting and varied example, powers of t. Same idea, we're going to look for what values of the power in the power t here will lead to convergence or divergence. And of course, we're going to start with our definition. If we have an infinity, we're going to let the upper limit be a number, and we're going to let that number go to infinity later. And I'm going to rewrite this as t to the negative k, because that'll make it easier to integrate. Okay, the limit as b goes to infinity stays around. Then when we integrate a power of t, we're going to get t to the same power plus 1, and then we divide by the new power. So it looks a little exotic, but it's exactly the same rule. If this had been t to the minus 2, we'd have minus 2 plus 1, divide by the new power, and we're going to evaluate that at the points 1 and b. Copy the limit, and minus k plus 1 usually better known as 1 minus k if we want that. And likewise, this would be b to the 1 minus k minus 1 to the 1 minus k. Well, 1 to the 1 minus k is just 1. There's a little bit of a fine print here that we should look at, though. Of course, we can't have k equal to 1 here, because then we would have it divide by 0. Though if we think about this case anyway, that would have been the integral of 1 over t to the 1. What's the integral of 1 over t? It's the one exception to this family. It would be ln. So that, with absolute values, sorry. So we'd have this different case anyway if we had the exponent 1 in our denominator here. We'll talk about that in a second. Let's look at this new form here and talk about what happens as b goes to infinity. Again, we're going to have cases. This value out here is just a number. What we're interested in is what happens as b gets larger and larger. In this scenario, we have b as the base, and b is getting bigger and bigger, so the base is getting larger and larger. So 2 to the 10, 3 to the 10, 4 to the 10, 5 to the 10, whatever. That's going to get larger and larger. 1 minus k is going to go off to infinity if the exponent is positive. So for example, if we had b to the 5 and we had b getting bigger and bigger, then b is going to go to infinity. So if that exponent is positive, or 1 minus k is bigger than 0, so we bring this over, and if 1 is greater than k, or usually we'd say k less than 1, so if k is less than 1, we're going to get the integral diverging, because our final value here is a larger and larger base to a positive power. We're going to get things blowing up. Then the other scenario is, I guess we don't need the if there, sorry. The other scenario would be if we had something like b to the minus 2. Well, if b is going towards infinity, we have larger and larger bases to the power negative 2. Well, that's like 1 over b squared. Well, that's going to go towards 0. Different scenario entirely. That's going to go to 0 if our exponent, and I know this looks strange, but it's just the exponent 1 minus k, if that is negative, or another way to write that is 1 is less than k, sorry, yeah, that's right, or k is bigger than 1 would be the usual way to write that. Then we're going to get the integral converging. So, we'll look at some scenarios here in a second, but we notice this very important distinction that if we have 1 over power t, it depends on what the power is. Some powers will converge, so if you have t squared, so this would be an example, the integral of 1 over t squared, that will converge. If we have a power k in the original integral that's less than 1, something like 1 over root t, that will diverge even though we still have the same kind of scenario. The integral gets smaller and smaller, the integrand gets smaller and smaller, and we get a function that goes down to 0. The area might still be infinite. Okay, so k less than 1 diverges. K larger than 1 converges if we're talking about integrals out to infinity. Last but not least, we have the less than 1, greater than 1. What about the k equals 1 case? Well, if you look at that integral, it'll be the ln case, and actually we saw that earlier. That integral diverges. So we actually have all our cases covered. If we have k less than 1 or equal to 1, then we get a divergent integral, even though the integral looks pretty much the same when we graph it out. If we have a larger than 1 exponent, so t to the 2, t to the 3, t to the 3.7, any larger power in the denominator there, then the integral, or the area underneath that graph, will be finite. The integral will converge.